In real oscillations, the mass eventually comes to a stop. If you pull back a pendulum and let go of it, as it goes back and forth, after some period of time, it will come to a stop. If you have a mass on a spring and you pull it and let go of it, even though it's on an air track with minimal friction, it will eventually come to a stop. It's moving through the air, so we know there's a drag force, and we call that type of motion damped oscillations. And here's the graph. It starts out with a high, or starts out with an initial maximum displacement A, and then as it goes through each oscillation, the amplitude decreases. So here they show the X max, delta change in X max, and as it continues oscillating, the change in X max gets smaller and smaller. If you connected those peaks, you get this dashed line they show here, and that's an exponential decay. And so X max is equal to the original starting value times this exponential decay. And the exponent here is it's e to the t minus t over tau. Tau is called a time constant, and we're going to take a close look at that. So let's look back here. These are for x over here. They substitute y over here, but it's the same mathematics. So exponential decay occurs when a quantity y is proportional to the number e taken to the power minus t over tau. Again, tau is the time constant, and this is the exponential decay, and they show the graph that goes along with that here. It says when t increases by one time constant, y decreases by a factor of 1 over e. What they show here is that one time constant, if you plot time versus amplitude, one time constant here means that a has declined to a over e, and they tell us that y has decreased to 37% of its initial value. We're going to take a closer look at that and see how that happens. If you look at the bullets here, at t equals 0, y equals a. If t equals 0, e to the 0 power, remember e is just a number, 2.718, and any number raised to a 0 power is 1. So if t equals 0, the exponent is 0, and the y value is simply a. As time increases and it reaches tau, when t equals tau, it says y is reduced to a over e. Well, let's take a look at how that happens here. It might be a while since you've worked with exponents. If t equals tau, you're going to have minus tau over tau, which is equal to a times e to the minus 1. And you might recall, you could rewrite that. If you wanted a positive exponent, you take that in the denominator, and so you have a is 1 over e. So if t equals tau, that's how you get y is equal to a over e. If you let t equal 2 tau, it reduces it by another factor of 1 over e, and you get a is equal to, the displacement's equal to a over e squared. Let me go to the next slide, and let's look at this ratio of t over tau a little more closely for an exponential function. I made a table here with different columns to look at this exponential function here. The ratio of t over tau is what I've made in the first column. The time constant t is fixed by the system. T is a variable. In this column, if we let t equal 0, then this ratio becomes 0. If we let t equal tau, then we get 1. So this would be t equals tau. Here, 2t, we let time go a little bit longer, 2t equals tau, the ratio would give us 2, and so on. As t increases, we get these numbers as the ratio. Now we take that number and put it as the negative exponent on this function and calculate it. So if you take e to an exponent of 0, we've said you get 1. If you take e to the minus 1, you get this number. We're going to round off to 2 digits. You can plug these in your calculator, and you go on down through the list, and you can see the numbers we get. If you plot these, let's make a plot here, and we're going to plot A. Now if we put A in front of our exponential decay, we plot A versus T, and let's just let A equal 1 in this example. That would be 1, and I'm not going to have room to really show this very well, but we want to plot this axis in 1 tau, 2 tau, 3, 4 tau, 5 tau. We start out here at t equals 0, our value is 1. At t equals tau, we're down to 0.37, so that would maybe be down here somewhere. And you just plot the rest of the points. At 2 tau, you're down to 14%. At 3 tau, you're down to 5%, and then 2%, and then 1%. Okay? As I said, I don't have much room, but if you graph that, you get an exponential decay like that. So the first time constant between here and here, that's 63%. You've dropped down to 37%, so you've dropped a total of 63% from the original position. And then the next decay between here and here would be 14%, and then 5% for the next interval, and then 2%, and then we approximate down to 0. So my amplitude decays down to 0 amplitude in 5 time constants. For the last section here, we want to talk about something called driven oscillations and resonance. What we mean by driven oscillation is the oscillation is subjected to a periodic external force. So let's say you have a mass on a spring like this, and as that's oscillating back and forth, you periodically give it an extra push. That would be a driven oscillation. Then you have a driving frequency. It's the frequency of the periodic external force. So you have a force that you're applying periodically, and the frequency that you apply the force is the driving frequency. Then we have the natural frequency of the system, and we saw that for a spring mass system. We had an equation to calculate the frequency. We would call that the natural frequency of the system. And then the frequency of a system, if it is displaced from equilibrium and released, it oscillates at that frequency. We put that at F0 there for the resonant frequency. And then resonance is when the driving frequency equals the natural frequency, and that's when you get maximum amplitude. So if I bump or push the mass at the driving frequency such that that equals the resonant frequency, that's when I get resonance and get maximum amplitude. Let's now look at the response curves of amplitude versus frequency, not time, but frequency. What they show us here is we have a system, and the maximum amplitude is when the driving or external frequency equals the natural frequency. So they're showing we have a system with a natural frequency at 2 Hertz, and if the driving frequency equals 2 Hertz, we get our maximum amplitude right there. If the driving frequency differs from the resonant frequency, they're saying if you drive it with the frequency out here close to 3, you don't get that much amplitude. You only get this little bit of amplitude here if the driving frequency, or what he calls here the external frequencies, not equal to that. And then he also shows that the damping factor, or the time constant here, plays a part in the response you get. Remember, this time constant's determined by the system. So it says a lightly damped system has a very tall and very narrow response curve. So this would be your time constant's 50 t. T is the period, and so you get a high response there, high amplitude. If you have a significant damping, you get a much smaller response. So this green curve is a time constant or a damping constant of 5t. You only get a small response like that. We'll talk some more about this in class and do a demonstration. Now we look at 3 of the reading questions that you should be able to answer these from reading the book. The type of function that describes simple harmonic motion, I hope you would know by now it's a sinusoidal function. Question number 2, a mass is bobbing up and down on a spring. If you increase the amplitude of the motion, how does this affect the time for one oscillation? Well, we've mentioned several times that the amplitude does not change the period, so that the answer here would be C. And the last one here, if you drive an oscillator, it will have the largest amplitude if you drive it at its resonant frequency. It will give you the maximum amplitude. That's all for the PowerPoints for this chapter.